Alright, so pretty much to solve all of these problems, you're gonna need to know essentially how to, if given the sine or the cosine function, you'll be able to derive the plot itself. And so just copy all this down, make sure you have this or know this, and this would help you out for all the problems. So pretty much if we have a sine that's multiplied by A is going to be our amplitude, which relates to the pretty much the height and depth of our sine function. Our T is going to be our period, so, and 1 over T is equal to our frequency. So if we have something that looks like 2 pi, or just let's say, like for this example, we have 120 pi T. To get the frequency of this is going to be 120 pi divided by 2 pi. Pi's will cancel, it'll be 60 hertz. That's going to be F. So F, our frequency, is in hertz. And our angular frequency would just be the 120 pi. So it's 2 pi times our frequency in hertz. Our phase is phi, which is going to be our phase shift. And looking at this example right here, we would have pi over 2 as our phase shift. Now, if we're giving a graph and it's just given, say, a time shift, so if we have something that looks like this, if we have a graph that looks like, let's just say, the sine graph starts here. Right here, we'll say this is equal to, let's just say 1 over 10 seconds. 1 over 10 seconds right here. This is going to be our time shift. So we're essentially having a time shift of 1 over 10 seconds. But we would relate this to our phase shift as multiplying this value times our frequency. So if we said our frequency is 120 pi, our phase shift would equal to 120 pi times the 1 over 10. And that's going to give us our phase shift right there. So this would be the phase shift of 12 pi. Alright, I don't know. Do you guys understand that? Do you have any questions on that? Does that make sense? Does it not make sense?
So 120 pi is the omega, and omega...
Yes. This is going to be our omega, right there, which we're pulling from right here.
Okay.
And the 1 over 10 is our shift. And we see that this shift was a shift to the right. And so if you have a shift to the right, you're going to have a negative sign right here. So this would actually be negative 12 pi. Would be that right there. I'll write that down. So,
because it's always minus the phase shift. If the phase shift is positive, it has to be.
if the phase shift is positive, it's going to the left. If the phase shift is negative, it's going to the right.
Okay.
All right, I'll write that down. You guys read that? Kind of small. Alright, so, this is just saying sine of the phase shift. So, the positive sign is going to shift us left, the negative sign is going to shift us right. So, just focus on that. Alright. Alright, now let's look at this problem right here. Let's look at 620. part A asks for the amplitude, the frequency, the period, the phase shift, the time shift. It's essentially everything we have right here. Of which one is it? V sub L. Of V sub L of t. So VL of t is equal to 12 times the cosine of 120 pi t plus pi over 2. Now look at this and looking at that, the first thing it asks for is our amplitude, A. So what's A equal to right here? 12. 12 is going to be our amplitude. And this is in volts, so our amplitude is actually going to be 12 volts. Now the next thing it asks for is frequency. And we're looking for frequency, but the first thing we look at is we see 120 pi t. That's going to be our angular frequency. So let's do that first. So angular frequency is equal to the 120 pi right here. So I'll just change this to omega. Omega equals 120 pi. Now, given omega, how do we get it to our frequency in hertz? What are we going to do to the 120 pi? Exactly. So our frequency, F, is going to be equal to omega divided by 2 pi. So this equals 120 pi divided by 2 pi. The pi's cancel. We're left with 60 hertz.
What do you divide by 2?
Divide by 2 pi. We come back here. Our angular frequency is going to be equal to 2 pi times F. And that comes back to the unit circle, because when we make a circle, it's in 2 pi, but I guess the best way of talking about that for a sinusoid, when you do a sinusoid, a full cycle of a sinusoid is 2 pi. 2 pi radians is going to be a full cycle.
Okay.
So if you want to get it in hertz, which is pretty much how many of those cycles is it doing in 2 pi, how fast are those cycles, you're going to get it in hertz. So you need to do for 2 pi.
So it's not always going to be divided by 2 pi, it depends on the sinusoid?
No, it will always, if you have your angular frequency, to get your frequency, it will always divide by 2 pi.
Okay.
So, and that goes for sine or cosine. Because essentially all a sine graph is a shifted cosine. I'll show you that in a little bit, it'll make more sense. Okay, and then it asks for the phase shift. So looking at this, what do we have as our phase shift? It's positive pi over 2. So we're looking at this sign, so it's going to stay positive pi over 2. And you would relate this this sign right here as your shift. So positive will shift to the left. If this was negative, then the cosine would shift to the right by pi over 2.
So the phase shift is pi over 2 to the left.
Yeah, this is positive sign is to the left.
Alright, that's what I meant.
Yeah. Okay. Now we're given the phase shift, and the final part of it asks us for the time shift. So how are we finding the time shift here? Exactly. So we're going to take this value right here, we're going to divide it by our frequency of our sinusoid. T shift is equal to P over omega, so this is equal to pi over 2 divided by 120 pi. The pi's will cancel, the 2 will come down into the denominator, so we'll be left with this equal to 1 over 240 seconds. Does that make sense? And you could think of it, the reason why we're doing the time shift, because we're plotting this across time. So if we have our phase shift, in order to get that time shift, we have to know the frequency of our sine, of our sinusoid, because that's telling us how fast or how slow this is repeating, pretty much. So we could have one with a large frequency, or with a small frequency, or we could have a graph with a very large frequency. So something that repeats and oscillates back and forth a lot faster than the original. So that's why we need to account for our phase, or our frequency, or angular frequency when we're talking time shift. Make a little bit of sense? Alright, part B asks us to plot one cycle V of t, or V L of t. So, how are we going to do this? If we look at this and we know that a regular cosine, let's just plot a generic cosine. I'm gonna have to do it over here, but I need to move this camera a little bit. Alright, so a generic cosine wave is going to look like this. It's going to start at its peak and go over here. And this is at 0. This is at pi over 2. This value is at pi. This is at 3 pi over 2. And right here, this is equal to 2 pi. That's how cosine, a generic cosine, we're not including amplitude or frequency here. So if we have a cosine and we're looking at a phase shift of pi over 2, we're going to shift this cosine to the right. No, to the left, I lied. We're shifting it to the left. So let's just redraw this, but with a shifted. This has shifted. So we'll say this is negative pi over 2. This is 0. This is pi over 2. This is pi. 3 pi over 2. And 2 pi. So if we're shifting this graph to the left, we're pretty much saying that this point at 0 is really going to relate to this point right here, pi over 2. So we can start the graph right here, and we're saying that the pi over 2 point, since we're shifting it by pi over 2, this point right here is going to be right here, at the 0 on this new graph. Make sense? Alright, so we would just do that for all the points. So this point down here would be right there. This point would be at pi. This point will be at 3 pi over 2. And this will come back down here. So this new shifted graph will look like that. So if we look at one cycle, say at 0, this now looks like what? Just taking that point. A sine, a negative sine wave. So this is upside down sine wave. So if we shift it, by shifting a cosine by 2 pi to the left, or pi over 2 to the left, we're essentially getting a negative sine wave. So a shift of pi over 2 from a cosine will get you a sine, depending on what way the shift is. It will either be a positive sine wave or a negative sine wave. And if you have a sine that's shifted by pi over 2, it's going to give you either a negative cosine wave or a positive cosine wave. Make sense? So, all right, this is our new graph now. If we're asked to plot this for part B. Now we have the general form of what this is supposed to look like. So how, now given our values, we have to pretty much create our amplitude and our period. So our amplitude from this is what? 12 volts. So we're going to have a value at 12 and a value at negative 12. Now we need to find our period. This one cycle is across 2 pi radians, but we want our period in seconds. So how do we get it in seconds? What's our period in seconds? How do we find period?
1 full cycle. That's your period.
1 over our frequency. 1 over f. Coming back to here. Our period is t, and t is equal to 1 over f. Make sense? You see that?
Yeah.
Alright. So I'll just write that. So our period is also equal to 1 over our frequency. That's important. So we come to our frequency, alright, we see that we're at 60 hertz. So our period for this inverted, or this negative sign in seconds is going to be 1 over f, which is equal to 1 over 60 hertz, which is in seconds. Hertz is equal to, a unit means a cycle per second. Hertz is cycles per second. So if you have 60 hertz, you have 60 cycles every second. So when you invert it, it's equal to 60 seconds. So if you take 1 over 1 hertz equals cycles per second. If we invert this, so we take 1 over hertz, we just flip this. So it'll give us seconds per cycle, which is essentially just seconds if we're only over 1 cycle. 1 cycle is 2 pi. So this pretty much describes everything we need. All we need is our amplitude and our period. And we have that. And if we wanted to find the seconds at each one of these points, we would do, we would just take this value, pi over 2, and we would divide it by 120 pi, which is our frequency. So it's similar to the same way we have our time shift, where it would be our phase divided by our frequency. So this would really be this value, which is a point in radians, divided by our frequency. And that will give us our time at that point. So this would be 1 over 240 seconds at that point. Make sense? Stop me at any point if it doesn't make sense. Alright, so that's part B. Now, part C is a little tricky. So, yeah.
What was the goal or question for part B?
Part B was pretty much just take these values right here, just plot the graph. So the first step I did, first thing I looked at was our phase shift. I originally drew our original cosine, just a generic cosine graph, and I implemented this phase shift, this pi over 2 phase shift to the left. So I took my values over here and just shifted this whole graph over. And I looked at it now from, instead of negative pi over 2, 0 to 2 pi. And then I went through this, found the amplitude, put our amplitude values in, and then the next step was finding the period. So we have our frequency, our period is just 1 over our frequency, 1 over 60 hertz, and that will give us seconds. So the 2 pi relates to 1 over 60 seconds.
Yeah, but like, how did you find the graph? Like, the scale?
What? The pi over 2, pi.
What, is it always that, or?
Yeah, just any generic wave. I'll just draw it out for a sine wave and a cosine wave. So one cycle for either one is going to be 2 pi. So 1 cycle of a sine wave or 1 cycle of a cosine wave is 2 pi. 2 pi radians. So that's for a sine wave. This is a cosine wave. And this is across 2 pi as well. So let's say the half point. Halfway point of that is pi. And the halfway point right here, right there, is pi. Now if you want to take half of pi, the distance between half of that, pi over 2. And the halfway point between here is 3 pi over 2. The same goes for this. So this will be pi over 2. 3 pi over 2. And 0. 0 again. And this is actually in radians, not time. So this is generic for all sinusoids. Yeah.
How do you find the time again at a certain point? So like 3 pi over 2.
Okay, so at 3 pi over 2,
Yeah.
we just take that point in radians, we
Yeah.
divide our radians by our frequency, our angular frequency. So it would be 3 pi over 2 divided by 120 pi.
Okay.
Alright?
Yeah, because it asks for like the earliest time where it's at its maximum.
Okay.
So,
So-
that'd be the 3 pi over 2.
Yeah, the earliest time it's at exactly.
After t equals 0. Right?
Exactly, where it's at its maximum would be
Okay.
right there.
Alright.
So that would be 3 pi over 2 divided by your 120 pi. That will cancel, so you have, what is this, 3 over 240 seconds. So that's going to be 3 over 240 seconds at that point right there. And that's your maximum.
Alright.
Does this make a little more sense? At least
Yeah, it does.
your generic version of it. Alright. Let's do part C, which is a beast. Eloise, I might be getting you in this picture. Yeah, let's move it over just so you can actually see everything. That's right. Let's move it. Alright, so part C is pretty much adding, we're saying we want to find V, which V is the combination of V sub R plus V sub L. So V sub R of T plus V sub L of T, and this is V of T. But we want it to be in the form of M, which is our magnitude, times cosine of, what is it, our angle plus, or our frequency plus our phase angle. So we need to add these, but one thing to note is that when you're adding cosines, the only way to combine two different cosines or two different sines is they have to have the same frequency. If they don't have the same frequency, you're not going to be able to combine them into one cosine like this. But because we do have the same frequency right here, the only difference is the phase shift. So we have to account for this phase shift. So adding this, we have
So if they have the same omega, they have the same
frequency, yeah.
Okay.
They have the same omega, they have the same frequency. Yeah.
Is the phase shift, is that still pi over 2, or are you just writing like that? Is it like
It's not part of the
The same
frequency.
frequency?
It's just part of your frequency is going to be a function of t. Okay, so because this phase isn't a function of t, it just constitutes a phase shift. Okay, does it make sense? So if you see 120 pi t, or if you see cosine of 10,000 t plus 5, right here, your 1,000 is going to actually, or your 10,000 is going to be your omega. It doesn't have to be just a pi. Your omega would be 10,000 in this case. Your phase is going to be equal to 5, or to 5. And if we wanted our actual frequency, we would actually divide. We would divide omega by 2 pi. So this would actually be 5,000 over pi. Would be our frequency in hertz. See how I got there?
Yeah.
Alright. So anything that's a function of t will be our omega, or our angular frequency. So we want to get it in the form of m cosine, or m times cosine of pi plus phi. But when we do this, v and r, we have vr of t, so v of t will look something like, let's just say vr 10 times cosine of 120 pi t plus 12 cosine 120 pi t plus our phase of pi over 2. So we can't just add these directly because we have this term right here. So we couldn't just add the magnitudes of them because we have this phase term right here. So we have to handle this. The only way to handle this now is we need to use a trig identity. So VL of t, which equals this 12 times the cosine of 120 pi t plus pi over 2. We're going to use a trig identity, which is, what is this specific identity? It's cosine, the cosine of an angle A plus B is equal to the cosine of A times the cosine of B, I think this minus sine. Let me look real quick. Alright, yeah, so minus our magnitude, I'll just say this is m, will be equal to m cosine of A minus m sine of A times sine of B. Now let's apply this trig identity to this right here. So applying this, we now have VL of t equal to 12 times the cosine, where this will be our term A, this will be our term B, cosine of 120 pi t times the cosine of pi over 2 minus 12 times the sine of 120 pi t times the sine of pi over 2. Now, we remember from the unit circle that what is cosine of pi over 2? Looking at, let's come back to the unit circle. Cosine of pi over 2 right here. 0. So this whole term's going to cancel. And the sine of pi over 2 is 1. So this is just going to look like, so VL of t is equal to negative 12 times the sine of 120 pi t. So now we got VL to look like this. Now if we plug this VL back into this equation up here, we'll now have V of t equal to 10 times the cosine of 120 pi t minus 12 times the sine of 120 pi t. And this will be equal to V of t. But this isn't our final answer. We want to get it into a form that looks like this. So going back to complex numbers, when we had our real component was our cosine component and our imaginary component was the sine value, how did we get the magnitude when we did this for just imaginary numbers?
Square root.
Square root of the real component squared plus the imaginary component squared. So if we want, we can do the same with this if we have it in the form of cosine and sine. So we'll say m is equal to the square root of 10 squared plus negative 12 squared. This is going to be our magnitude m of this equation. So this is equal to 15.62 volts. 15.62 volts. And our phase angle, theta, or I have it as phi up there. Phi, how do we find the angle using, when we had complex numbers in rectangular form?
Tan inverse.
The tan inverse of our,
Negative 12 over 10.
yup, exactly. So we have the tan inverse of negative 12 over 10, which gives us an answer of 50.2 degrees. So now we have our m and our phase, and we can put it in this form now. So our final answer, V of t, would equal to 15.62 times V of t equals 15.62 times the cosine of 120 pi t plus 50.2 degrees. That's going to be our final answer for C. So alright, this was a little difficult to go from here to here. But let's just go back and look at the steps what we took to get to this point. So we're adding V sub r of t and V sub l of t, and we have that as 10 cosine of 120 pi t plus 12 cosine of 120 pi t plus pi over 2. So looking at this, the only thing that's given us an issue is this phase shift, this pi over 2 phase shift. So how do we handle this? We handled it by using a trig identity. This trig identity right here. So by adding these two, we were able to break this up into something that looked like this. 12 times the cosine of 120 pi times our phase shift. This allowed us, because we had a phase shift of pi over 2, this allowed us to cancel this term and get this into a sine. So that we can then bring V of t to look like the cosine minus or plus a sine. Yeah.
Should things always cancel out when you're doing this type of stuff?
They won't always cancel. And you got lucky because it's pi over 2. If you have a pi over 2, it will cancel. Because that's going to be, it's going to contain all of your sine values. Pi over 2. Just coming back to the answer. So that's pretty much just the methodology and steps to take in order to solve this problem, to get it in this form. Because once we have it in this form, we remember from complex numbers how to find the magnitude and how to find the phase, right? Quick refresher. Are we good on that? We're good? Alright. Alright, so this was 620. And 623 pretty much did the same thing for part A. So let me just go through part A of 623, and then we can go over some of this Matlab stuff. Give you some time to write this down too, if you... Are we good with this section over here? Go with this section.
Part A of 623, you're going to have to use the trig identity to change I of 2, right?
Yes.
And then you should do the same thing, find the n.
Yeah, to find the ends. But the trig identity is going to be a little different for this one because this is sines versus cosines. So the trig identity with sine is a little different than with cosine. I'll give you that in a little bit. He didn't go over any of the trig identities or anything?
I think it's by system.
Okay. For the next, I guess for the next exam, if this is on the cheat sheet, make sure you write down all the trig identities. Make sure you have this down too, and just so you're not, I guess, trying to think back or remember and waste any more time, because obviously time was pretty crucial for that exam.
It didn't even start with
Alright, so we have I of R, I sub R of T, and this side inductor, this side resistor, I sub L of T, and we're saying that I sub L of T is equal to 10 sine, 10 times the sine of 120 pi, I believe. Is that right? 120 pi t minus pi over 2?
Yeah.
Alright. Minus pi over 2. I of R of t is equal to 10 times the sine of 120 pi t.
They had it labeled differently.
Did they?
They had it I of 1 and I of 2.
I have 1 and I have 2. Alright.
Is it the same thing as also I of L and I of L?
Yeah, this would be your I of L. Whatever they have pointed down.
Yeah.
What is that in the book? I have 1.
Yeah.
I have 2. They have that as, so this is equal to I of 2, which is I of L. The only reason I'm saying L is for the inductor, because
Okay.
this is the current across the inductor, this is the current across the resistor. So this equals, so I of R they're saying is I of 1 of T, and this one, I of 2 of T.
Yeah.
Alright. So, we want to get it again so that I of T is equal to IL of T plus IR of T. And we want to get it into that form again, so that it will be m times the sine of 120 pi plus v. So we want to do, so what, from this, what was the first step that we want to do? What was the first step we did right here? Trig identity onto the term that had the phase shift, right?
Yeah.
Okay. So the trig identity for this is the sine. This one just starting to die. sine of A plus B is equal to, is there a glare? Can you see this? Is this fine? Alright. So the sine of A plus B is equal to, or M times the sine of A plus B is equal to M times the sine of A cosine of B plus M times the cosine of A times the sine of B. M times cosine of A times sine of B. Alright, so applying this trig identity to this term, the I sub L term, we're going to get I sub L of T. Alright, let me move this over here a little bit more. So. This is a trig identity you're going to want to know, and this is a trig identity you're going to want to know. So write those two down. So I of L, by applying this trig identity, we have I of L equals, coming back here, 10 times the sine of 120 pi t times cosine of negative pi over 2 plus 10 times the sine, or cosine, of 120 pi t times the sine of negative pi over 2. So we have this out as I sub L of t. So looking at this, is there anything that's going to cancel? First term, the cosine of negative pi over 2 is going to be 0, which is going to cancel out this whole term. So that cancels out the whole term. So I L of t is equal to, okay, and the sine of negative pi over 2 is equal to what?
1.
Negative 1, because of that negative term. Because this will be on the unit circle, negative pi over 2 is right there. We're going that way. So it's going to be negative 1. So this I of L term is going to be negative 10 times the cosine of 120 pi t. And now we have one term that's a cosine, another term that's a sine right there. So we will now make I equal to I of t equal to I L of t plus I R.
Wait, why did the sine of 120 pi t cancel?
The sine of 120 pi t
Up there.
cancel with the cosine?
No, like, yeah, why did it cancel when you brought it down?
They won't cancel because of the phase shift, because you would have it. See, I think our sines are actually going to, let's look at it. Alright, if we have sine, if we have 10 sine,
Oh.
10 sine and then a negative cosine.
Oh, never mind.
You good?
Yeah, it was because the cosine of pi over 2 is 0.
Yeah.
Yeah, I didn't get that.
Oh, you were talking about this
Yeah,
term
that's
right
what I was
here?
talking
I'm
about.
sorry. Yeah, the cosine of negative pi over 2 is going to cancel.
Yeah.
So this will look like, I of t is going to look like negative 10 times the cosine of 120 pi t plus 10 sine of 120 pi t. Now we have it in this form right here. we want to find our magnitude and our phase. So how are we going to do that?
Square root of -10 plus square root of -10 then.
Yep. Square root of -10 squared plus 10 squared. This is going to give us square root of 200, which is equal to 14.14. Now our phase, how are we going to do this? Finding the phase. Tan inverse. Yep. Tan inverse of 10 over -10, which is going to be equal to -45 degrees. And then B is pretty much asking to find the amplitude, frequency, phase using this. And I want to show you guys some Matlab stuff, so are you guys all right with this? Do you have any questions? I know it might be a little overwhelming all that at once, but just remember if you're looking at a problem like this, let's go through our steps. Our first step is we're going to find, if they're both sines, we're going to find the one that has a phase. So we're going to find the sine that has the phase shift, and we're going to apply some type of trig identity to it. The majority of the time, if he's given a problem with phase shift, it should be pi over 2, just so you can cancel terms like this. But we find the sine with the phase shift. We apply our trig identity, which was right there, to get it into this form right here, and then we're able to see one of these terms should cancel. The cosine of pi over 2 should cancel. We'll cancel that term and will give us purely a cosine term. So we want to pretty much convert one of these, mainly the one with the phase shift, into a cosine, so that we can find the magnitude and the phase. Make sense? Alright, so find the one with the phase, apply the trig identity, get it into a form of a cosine and sine, find your magnitude and your phase. That's the method.
What's the equation for magnitude?
Magnitude is just going to be the same as it was with complex terms. So it was you could think of it as your imaginary term, because sine in our rectangular form of complex numbers was the imaginary term. So it was our imaginary term squared plus the real term squared, and the square root of that. Because if we go back to complex numbers, we would have x equal to, magnitude of the sine, or cosine of some angle, plus j and sine of some angle. We found our magnitude to polar form when we converted to polar form. So converting to polar form, we took the magnitudes in each. So if I say A and B, the magnitude of this was equal to the square root of A squared plus B squared. Okay? That gave us our magnitude, and our phase was the inverse tangent of our sine term, or our imaginary term, inverse tangent of B over A. Alright? Alright, let's go over some Matlab stuff.
Should we take notes for this part?
On the Matlab stuff, I would say take notes just so that you remember. You don't have to. It might be better if you guys want to pull up Matlab, do it, and save the file and send it to yourselves. So if you guys want to get in front of a computer, open up Matlab and we'll just all do it.
That's a great idea.
Yeah. Yeah, we'll record the Matlab stuff too. let's just create a sine.
Cramming is the way to
Create like we'll create the plot given like the amplitude, the frequency, the period, and we'll create that. Yeah, we'll create it across
It's like magnitude times cosine of theta of t.
yeah.
One of the figure will show the difference between like magnitude and stuff.
Yeah. I know.
Are you on the screen? So you don't actually have to be able to damn it like the map.
Yeah. I don't know how. Does everyone have Matlab open?
Is that everybody?
Alright, so let's just do it for the first problem. What was the first problem of chapter 6? 6-8? Alright, well let's go with 6-8 though, because we have the graph, so we can compare our graph to the graph that's there. Alright? So for 6-8, it's giving us, actually all it's doing is giving us the graph, it's not giving us the amplitude or frequency.
Did we do 6.5?
Yeah, let's do 6-5 then. Alright, so 6-5 we have,
possible make a font.
yes. We'll control shift. Hold up, give us a second.
Nope, okay, so this right here, I can't highlight it, but this is where your home directory is. So if you actually look in your window, you see that we're under C, and we go to users, and this, documents, Matlab. So we can see that it already created a new text file called 6.5. So you do the diary, and then in parentheses you do ticks, and then whatever you want the file name to be. So if I open this, it's just going to be a blank file right now, so I'm not going to do
Well,
that.
you might not be able to open that because that's saying file, a 5 file. And the reason why is because it has 6.5 and it thinks your extension is this 5. So if you name it, make sure you name it some name.txt as a text file.
Yeah, you're right. We'll open. Alright, so let's do that again. So
Just
we
do
do,
diary
yeah, we do diary off, it turns off the diary.
.txt.
Or you could do a docx.
docx, which
That'll
is a
be-
Microsoft
yeah.
Word file.
Alright,
So what happens if you just do not DX?
If-
what's that?
What happens if you don't write docs?
It'll just save it as a text file, and then it'll give you options to open it whatever you want to.
Yeah, I think by default it will save it as a text file. I'm not sure if you just called it 6_5. I think it would assign it a .txt file extension. Not 100% sure on that, but it,
Just try it.
Yeah, we'll
That's
take
what
a
I'm
look.
at. We just do it like let's do 6. So if you write that, and then we look at this again, you create 6_6 as a file, and if I click on it, it asks me how I want to open it. So I
Alright,
can say open in Word,
Word.
and then it asks me if it's a read only because it's not written yet. So we'll just close that out.
But if you want to be safe, just make it a .txt file extension. That way it will know by default what to open it up with, whether it be WordPad or whatever you have your default text editor as.
So the first thing it gives us is our frequency theta. So we can do theta equals 3 times pi divided by 4. So Matlab is really cool because it knows what pi is. It'll use like 3.14159 to a whole bunch of decimal points. Make sure you terminate everything with a semicolon, because if you don't, you're going to get a whole bunch of outputs. But if we put a semicolon there, it tells Matlab to suppress the output, and it doesn't write anything. So it just makes the code look a little neater, and it'll look nicer in your Word document.
And another thing to mention is right now we're working in the command window. So it's going to execute stuff. It will execute stuff in the command window. But if we want to just create everything in a script and then execute it, it will display it on the command window. But we can do everything in a script by pretty much going to up to the top and go in,
Just like edit.
or you can do edit. Just type edit, and it will bring you to your script, and you can do everything within your script right here. And it will display your results down
But
here.
He wants, this is for Dr. Bond, he wants it in a diary.
Oh, he will. Well, can you do diary in this?
I don't know. I don't know. You can just copy and paste in the script editor.
Yeah.
We'll just work in the command window for now, make
Yeah.
it easier.
You need help.
So the next, if we just keep reading on, we see that at time equals 0, and it takes for 2 seconds. So it really wants from time 0 to time 2. So we need some kind of array that goes from 0 to 2 and gives us a whole bunch of points in between. Does anybody want to take a guess as to what the function is? Good. So we do t equals linspace from 0 to 2, and then if I type 1,000, does anybody know what that means?
1,000 points.
Yeah, gives 1,000 points that are equally spaced apart from 0 to 2. So I'm going to hit a semicolon so we don't goof it all up. Now if we look into the workspace, we can see we have a variable that's an array of 1 by 1,000 that goes from minimum 0 to maximum 2. If we double click on this, it'll open up and we can see all the values of our new array called t. The workspace, you just click on the variable t in your workspace. And that's helpful when you have smaller arrays, but don't waste your time checking each part of a 1,000 number array. It's just a waste of time. So after that, we see that it does a full rotation in those 2 seconds, and we have magnitude of length equals 15. So now we have 3 new variables. One's called theta, one's called t, and one's called L. So we can create a new variable to plot this as a cosine. We call it x equals the length, which is our magnitude, times the cosine of theta, which is our frequency, times t, which is our linspace vector. Right? If we do that, it'll give us this new array called x that's 1,000 wide. So we have 1,000 more things, 1,000 more data points that come from t and theta using the cosine function in Matlab. Right? So if we want to look at this on a plot, we can type plot, and then the way Matlab does plot, it does your x-axis versus your y-axis. So on our x-axis, we want our independent variable, and for this case, it's t. So you want to do t first, and that'll plot your 1,000 points from 0 to 2 on the x-axis. Then the y-axis is the dependent variable, which is going to be x, because that's what changes compared to t. So if we just type enter, we get a cool little plot that shows our cosine. And typically cosine oscillates between 1 and -1, but we can see that because of the magnitude adjustment, which we have as L, we actually go from 15 to -15. So if we wanted to do something else and see how the magnitude is affected, we can create a new variable called y, and we can just do the cosine of theta times t, and we can plot that. Now, if you want to look at everything all at the same time, there's this little button up here from your figure, and you can dock your figure so it'll sit there the whole time. Another cool function in Matlab is called hold on. So hold on works with plots. So if I type hold on, it'll hold all the new plots that I type. So then if I type plot t comma y, And then I want to make it so that the plots are different colors. So if I do another comma and I do in ticks R, it's going to plot me a red line that now my y is, the new y-axis is the new cosine theta times t. So if I plot that, you can see the difference between what a regular cosine with no scaling would look like and our scaled one. And it looks like it's almost a straight line because the magnitude is actually 15 rather than 1. You guys have any questions as of now? No? Okay. So,
There's also confusion between some
And then where is it asking?
you guys know what the figure looks like for the question itself, right? You all have the book with the question? No? I can draw this. So, So what the question's asking us to plot with Matlab is it wants your x and your y components as a function of time. So how would we go about doing that? You guys know? What we've been working on for most of the class, right? Right, we're given this angle here is 3 pi over 4, so we can calculate what this angle is, right? We can calculate this angle theta. Right, so how, if we have this angle theta and we know the magnitude, how will we solve for this side? Sine, okay. We have 15. We have y equals 15 times the sine theta, right? And this one is x equals 15 times the cosine theta. So theta is pi minus 3 pi over 4. You all see where that comes from, right? Theta. Anybody see where that comes from? Everybody, right? So, with Matlab, you can overwrite all of your old functions. So you can just say now that theta equals pi minus 3 times pi divided by 4. So that gives us our new value of theta as 0.78, which is just pi over 4. Right, so we want to find x and y. So we can set a new value of x that's equal to length, because remember we have length is 15, times the cosine of theta. And then times t, because we want it as a function of time. And then if you tab up, guys, you can redo your commands from earlier. You can go back through them. So just to be lazy and have a shortcut, we can erase that and type sine and change the x to y. So now we have two new functions, called x and y, that will give us our x and y components of this figure right here. So then with plot, you can also plot two things at the same time. So we can do t comma x comma should work. Plot is green, and then we can do t comma y. Plot that one. Oh. Gotta turn hold off, otherwise it'll plot everything with it.
See a plus sign.
Do you see cosine?
See a plus sign.
Good. So now we can see that our x component is the green graph, and through 0 to 2 seconds, that's the track that our x-axis is going to follow, and our y-axis is going to follow the track. So that's the first part of 6.5. Everybody following so far? Did I lose people? Anybody have any questions at all?
What's the whole plot thing? I don't understand what you put in the parentheses after plot. What's the meaning of all of that?
Okay, so plotting. Alright. So the t is the lin space, right? T is that lin space from 0 to 2 seconds with 1,000 points there. So that's going to be our x-axis because we want to see what happens within the first 2 seconds. That's what the question is asking for. Right? Dot x value is the x equals cosine, or L times cosine of theta times t. So that's how our x component of this function is going to move in those 2 seconds. You're plotting the path of the x component. It starts at 15 and goes all the way down to 0.
Alright.
Okay? And then this tick green, that just changes the color of the plot. If I didn't do that, it would plot
Oh,
as
and then the
blue.
other one's red.
Yeah, the other one's red. If I didn't do that, it would plot them both as blue and it'd be harder to see.
Okay.
Alright?
And then the other one's the same thing, time and then
Yeah, time, then the y function, and then red.
Yeah, let's do it. So,
Solid where you
No.
we don't now there are where you at?
Yeah. What do you want?
Just keep going to questions.
Okay.
And when I run this, because I use a semicolon, I execute it each line.
Okay, so can you guys tell me what is the amplitude? The amplitude? 15? It's 15, right? Because it says that L equals 15 centimeters. So I don't know why it's asking you guys for the amplitude in the question. What's the frequency? What does frequency equal? I think we did it over here.
You want to be 1 over 2, like 1 over 2? 1.5?
Well, okay, so the amplitude is the height of the curves. Okay? The frequency and the period are related to each other. We're calling amplitude L in this problem, and we're calling the period and the frequency. So in this problem, T represents time. So how much time has passed? Do we know how to calculate how much time has passed? Like what the period of?
I think we said it's 2.
It would be what?
We said it's 2.
2?
Yeah, because that's like.
Would it be 2 or 8? Because you have to like do the whole.
Right.
The whole
Well,
weight.
we'll just.
The whole weight. Only a quarter would do.
I would say it's 2 here. I think because I'm saying. I don't know. Yeah, 2 seconds. Okay. So we're just looking at this one section of time. So in this section of time, if T equals 1 over the frequency, let me think about how to write this in Matlab. So, do you have any ideas of how you would write the frequency in Matlab?
1 over 2.
Okay.
You just say F equals 1 over 2.
F equals 1 over 2. Yeah. Do you have T, and T as a defined variable? Yeah. So you would just say F for frequency equals 1 over T. And what's the phase angle? What's the phase angle of this? Does anyone have an idea what the phase angle could be?
3 pi over 4.
3 pi over 4.
Isn't that what they said?
Well, they said that it takes 2 seconds for the robot to move from 3 pi over 4 to 3 pi over 4 plus 2 pi, which means basically that it's going in a complete circle. So the phase angle of that,
Because it doesn't start at 0, it starts at 3 pi over 4. So it goes at 3.
what is it? Sorry. I might have a different idea of what that is. What are, when you're saying phase angle, what do you mean?
Isn't that like the shift to this? It's like the robot didn't start at 0, it started at 3 pi over 4.
So the phase angle is where it starts?
Yeah.
It's where it starts?
Yeah.
Okay. Okay, then yes, it is.
Is that it?
Let's ask you really quick because my impression of a phase angle is like that it's the whole thing. Okay.
You're right. Great. Sorry for that.
Okay. So if the period here is 2 seconds, what is the time shift?
The big thing to just using is probably
All right. So far.
Alright guys, it seems like I'm running out of time a little bit.
I'm sorry.
It's alright. I know it's confusing. I just read it a couple times and it didn't make sense to me. But hold up. Do you guys got time? I mean, if you don't got time, you can roll out. I'll do this real quick.
When it's asking for the amplitude, are they just saying
The
like
left.
like
L.
well, are they supposed to be doing answering all these questions on Matlab? Like, are they supposed to just be plotting on Matlab, or are they answering all these questions on Matlab? Oh, really? So, but they already have like L equals whatever. So then I said, well, okay, so if L equals that, but like if the what's the period? 2 seconds. I was like, okay, so what's the frequency? Okay.
Alright, so that's how we'll do it.
Okay.
Alright guys, I'll try and run through this real fast. Yeah.
When I tried downloading Matlab, like you download that trial or what do you?
No, go to did you go to the Temple Download Center?
Yeah, I went there and I went like which software? It just says the software. There's like plenty of Matlab software. There's one for students that you have to buy.
I mean, I put a lot in that, but
These are stupid questions. Everything you put in, you don't need math. And it
it's so
overcomplicates everything.
yeah. And they're like answering my questions, and I was like, I think like. I don't know how they would write any of that stuff in Matlab except just to say like.
Well, you can do like the, so you know the period is, you know the frequency is 2 seconds. It goes through one cycle every 2 seconds. So you can calculate the period by doing
Right.
whatever.
Well, we got that far, and then like doing the phase angle was like confusing because
There's a way to do it. Matlab has like Alright, get out of here. See you later.
I can't commit to it.
That's fine.
Okay. Alright, thanks.
Look on the presentation tomorrow. Because we'll go over it again tomorrow.
I have no idea what you're doing.
Well, I can try and set up all the sets. Was actually one if you can call to this is what we live on campus.
Might be able to hear.
Yeah.
Yeah, I could hear. Dude,
I know
I didn't do the last call, I had no idea to do it.
Yeah.
And my other friend who lives in my dorm, and he was like, yeah, I kind of did it, but
Yeah, that's what I'm saying.
yeah, I'll come around.
Yeah, no problem.